Hey everyone, welcome back to the Horizon Robotics Lab. Today marks your first problem set solution guide. We're walking through a few essential problems to really master the basics. We're talking Ohm's law, parallel and series circuits, and how to calculate power. Again, like always, we're going to break down each problem step by step so you truly understand what's going on behind the numbers. Let's jump right in. Like in our discussion, we're starting real simple. We're talking about a resistor in series with a battery. We have a resistor with a resistance of 10 ohms, which is connected to a 6-volt DC source, or a 6-volt battery. This problem is asking us to calculate the current through the circuit. It wants us to calculate the voltage drop across the resistor and the power through the circuit from the source, the battery. Cool, let's go ahead and get started. To find the current I, we first need to start with Ohm's law. And remember, Ohm's law is V equals IR. If we rearrange the equation to solve for I, we have I is equal to V over R. Very nice. So V in this problem is 6, and then R1 is equal to 10 ohms. So now if we plug that in, we have I is equal to 6 over 10. And so that means we have 0.6 amps flowing through the circuit. Very nice, strong start. Now we want to figure out what the voltage drop through the resistor is, or V1. So V1 is equal to I times R1, given by Ohm's law, as always. So we have V1 is equal to 0.6 times 10. So V1 is 6 volts. So the voltage drop through the resistor is 6 volts. And that makes sense because the resistor is the only thing getting voltage in that circuit. Now the last part is to find the power coming from the source. Power is given by voltage times current. The voltage from the source is 6 volts and the current coming from the source is 6 amps. So this tells us it is 3.6 watts. There we go. Very nice. Cool. So we answered all the questions in this problem. The current through the circuit is 0.6 amps. The voltage drop through resistor 1 is 6 volts. And the power flowing through this circuit is 3.6 watts. Everything here looks good and everything makes sense. Let's move on to the next problem. This time we have 3 resistors in series. And again, like always, we know that they're in series because it's one after the other with no parallel paths. So, reading the problem, we have 3 resistors, R1 with a resistance of 10 ohms, R2 with 20 ohms, R3 with 30 ohms, and they're connected in series to a 6-volt source. We want to calculate the total resistance, the current I, and the voltage drop across each resistor. Let's go ahead and get started. So let's just write down what we're given first in each problem. So V is 6 volts, R1 is equal to 10 ohms, R2 is equal to 20, and R3 is equal to 30 ohms. There we go, just adding the ohms on each one. So when you have a series circuit, the total resistance is given by the sum of all resistors in series. So if we want to find our total, next to that, our total is equal to R1 plus R2 plus R3. So we have 10 ohms plus 20 ohms plus 30 ohms, and that is equal to 60 ohms. Beautiful. So now we have our total is equal to 60 ohms. Very nice. So now we need to find what the current is in this circuit. And you guessed it, Ohm's law once again. So we have V equals I total, call that I total, times R total. There we go. Rearrange the equation, you find I. So I total is equal to V over R total. So that is 6 volts divided by 60 ohms. So I is 0.1 amps, or 100 milliamps. There we go. Both work. Very nice. Now let's calculate the voltage drop across each resistor. Again, we're going to be using Ohm's law, and in this instance, we're going to be using I total for each resistor, and that's because in a series circuit, the current is the same through every component. Let's start with the voltage drop through resistor 1, and again, like always, we're starting with Ohm's law. So, V1 is equal to I total times R1, which is equal to 0.8 amp times 10 ohms. And that is 1 volt. V2, the voltage drop through resistor 2, is equal to I total times R2, 0.1 20 ohms, and that is 2 volts. Now, finally, V3 is equal to I total times R3, which is 0.1 amps times 30 ohms. And that is 3 volts. And to make sure that we did everything right in this problem, if we sum up the voltages through every resistor, it should sum up to the voltage of the source. So if we add V1 plus V2 plus V3, it should be equal to V source. And in this example, we have 1 plus 2 plus 3, and is that equal to 6 volts? Yes, it is. 3 plus 2 is 5, plus 1 is 6. 6 equals 6, so everything checks out. Very nice. Next, we switch to a parallel circuit problem. In this example, we have 2 resistors, one with a resistance of 10 ohms and R2 with 40 ohms. Those are connected in parallel to a 6 volt source, and the problem wants us to calculate the power dissipated by each resistor, P1 and P2, and the total power delivered by the source. Let's jump right in. Alright, let's always start by writing down what information is given to us. So, we have the V is equal to 6 volts, we have R1, which is equal to 10 ohms, and we have R2 is equal to 40 ohms. So the problem wants us to find P1 and P2. P1 is given to us by V times I1. And P2 is given to us by V times I2. There we go. So since we don't know what I1 and I2 are, that's exactly where we need to start. In a parallel circuit, the voltage drop through each branch is the same. So we know there are 6 volts going down this branch and 6 volts going down the other branch. So if we use Ohm's law, we could definitely find I1 and I2. Let's check it out. So I1 is given to us by V over R1. So we have 6 volts divided by 10 ohms, and that is 0.6 amps. Very nice. I2 is the same. We have V divided by R2. That's 6 volts over 40 ohms, and that is 0.15 amps. Very nice. We now have I1 and I2, so we can find out what the power is through each branch. So P1 is equal to V times I1, so that's 6 volts times 0.6 amps, and that is 3.6 watts. There we go. Now for the second branch to find P2, it's the exact same. So we have V times I2, and that is 6 volts times 0.15 amps, and that is 0.9 watts. Ta-da! There we go. We now found the power going through each branch of our parallel path. So now we're on to the last part. We need to find out the total power flowing through the circuit. Well, to find the power going through the circuit, we can just sum up the power through each individual branch in the parallel path. In other words, we can sum up P1 and P2. So P total is equal to P1 plus P2. So we have 3.6 watts plus 0.9 watts. And that gives us 4.5 watts. Great job. So we got some pretty big ideas here. For example, the voltage through each path is the exact same. Not only that, but the current splits through each path depending on the resistance. And last but not least, you can sum up the power through each branch to calculate the total power running through the circuit. Now, we have a mixed series and parallel network circuit here. The problem says we have a 6-volt DC source connected to we have a 10 ohm resistor in series with a parallel combination of 20 ohms and 30 ohms. Well, for starters, we know that this is the parallel path, or the parallel combination, and this guy is in series with that parallel combination. In this problem, let's solve for the total current in the system and the voltage drop across each resistor. So first, when you have a mixed series parallel network, you want to first simplify the parallel connections. So we're going to first simplify this to get the equivalent resistance of the parallel connection and then solve for an in-series circuit. Much easier. Let's start by writing down all the information that's given to us in the problem statement. We have a voltage equal to 6 volts. We have R1 equal to 10 ohms. We have R2 equal to 20 ohms. And R3 equal to 30 ohms. There we go. First, let's simplify our parallel connection to get the equivalent resistance. So, 1 over R equivalent is equal to 1 over R2 plus 1 over R3. There we go. We have 1 over 20 ohms plus 1 over 30 ohms. Very nice. So when you have it like this, you want to try to simplify it as much as possible. So we're going to multiply each side by 1, technically, and get it to the same denominator to make adding them up easier. Let me show you real quick. So you multiply 30 over 30, there we go, multiply that, and you multiply this 20 over 20. With this notation, we're just multiplying by 1. We're not changing the values in any way, shape, or form. We're just changing the way that they look so that they have the same denominator to make the addition much easier. And if you're unfamiliar with this notation and you would love for us to do an algebra review, feel free to message us at Cristobal@horizonroboticslab.com. The more I see, the higher likelihood I'll do it for you guys. Now we have 30 over 600 plus 20 over 600. So now we have an R equivalent of 50 over 600. If we flip that fraction, we get R equivalent is equal to 600 over 50. And that is just 12 ohms. So our parallel connection is really just 12 ohms. And we'll redraw that in a simplified form in just a second. So if we were to redraw our circuit, replacing the parallel combination with the R equivalent resistor, we'd have 2 resistors in series, which is much simpler to solve for. When you have 2 resistors in series, as we always remember, we add up the resistance. So R total is equal to R1 plus R equivalent. And this means we have 10 ohms plus 12 ohms, which is just 22 ohms of resistance. Beautiful. So now if we redraw the circuit one more time, substituting the resistors in series as just one resistor with resistance R total, we can use Ohm's law to find the current and whatever else we need. So if we want to find the total current through the circuit, we want to use Ohm's law, of course. That is V equals I, I'll say total, times R total. So I total is equal to V over R total when we rearrange the equation. Our V is equal to 6 volts divided by 22 ohms of resistance. So our total resistance is equal to 0.273 amps. Now let's figure out what the voltage drops are through each resistor. So through V1 we have I total times R1, and that is 0.273 times 10 ohms. So V1 is approximately 2.73 volts. Awesome. So through our parallel connection, we would expect that it's just 6 minus the voltage drop through that series resistor. So V parallel is equal to 6 volts minus 2.73 volts. And that is, with the help of our calculator, 3.27 volts. All right, that is what it is. Beautiful. Cool. So through our parallel connection, we are eating up 3.27 volts, and through our series connection, we're eating 2.73 volts. Here's another mixed series parallel network combination circuit. This problem says a 6-volt DC battery is connected to a network of resistors. A 220 ohm resistor R2 is in series with a 330 ohm resistor R3. That series combination is in parallel with a 100 ohm resistor R1. Let's start off by writing down what the problem statement has given us. So we know that the voltage in our circuit is 6 volts. We know that R1 is equal to 100 ohms, R2 is equal to 220 ohms, and R3 is equal to 330 ohms. Very nice. Cool. The goal of this problem is to figure out what the total current is and what the voltage drop through each resistor is, like the previous problems we've been doing. Whenever I have a mixed series parallel combination circuit, what I always like to do is I like to start with the parallel connection, but only when the paths are simplified. What I mean when they're simplified is there's only one resistor in each path, right? In this scenario, we have a series connection in one of the paths, so it's not completely simplified. We have room to simplify here first. So what we need to do first is to get the equivalent resistance of that series circuit in that path, and then we can actually move on with simplifying the parallel connection. All right, so let's calculate the equivalent resistance of those series resistors. So the equivalent resistance is equal to the sum of the resistors, R2 plus R3, that's 220 plus 330, which is 550 ohms. So if we were to simplify this circuit, we'd have a 6-volt battery connected to 2 resistors in parallel. So we have R1 on one branch, and then we have R equivalent on the other branch. And now we have a simplified parallel circuit, so we can combine that into just one. All right, now let's calculate the total resistance in this circuit by simplifying the parallel combination. So we have R total, don't forget the 1 over that one, is equal to 1 over R1 plus 1 over R equivalent. So that gives us 1 over 100 plus 1 over 550. Again, like before, we're going to multiply by 1 by multiplying it by the opposite numerator. So in this instance, I'll multiply 100 over 100 to the 1 over 550 side, and then 550 over 550 to the 1 over 100 side. And that'll make it such that they have the same numerator. So now we have 550 plus 100 over 55,000. There we go. Very nice. So 1 over our total is equal to over 55,000. If we flip that fraction, we'll actually get the real R total. So R total is equal to 55,000 divided by 650. And that is an equivalent resistance of 84.62 ohms. So now that we've calculated the total resistance in the entire circuit, we can simplify this even more. We can now simplify the entire circuit as a single resistor in series with a battery. Now that we have that, we can calculate what the total current going through the entire circuit is, and then we can find out what the voltage drops are through each circuit. To find the total current, we obviously need to use Ohm's law once again. We have V equals I total times R total. So if we change up our equation, we have V over R total. The voltage is 6 volts and our resistance is 84.62 ohms. That tells us that our total current is 0.0709 amps or 70.9 milliamps. Okay, the total voltage through each branch is 6 volts. Let's calculate the current through each branch. So through branch 1, we know I1 is equal to V over R1. So we have 6 volts divided by 100 ohms, and that is 0.06 amps. Very nice. To find I2, we're going to use the equivalent resistance that we found from adding the resistors in series together. So I2 is equal to V over R2 plus R3, which is going to be equal to 6 volts over 550 ohms, which is roughly 0.0109 amps. Very nice. So now that we have the total current going through I2, we can figure out what the voltage drop through each resistor is going to be. So let's find out what V2 is. V2 is I2 times R2, and that is going to be 0.0109 amps times 220 ohms, which is approximately 2.40 volts. And then V3 is going to be I2 times R3, which is 0.0109 times 330. And this one is approximately 3.6 volts. And now if we add these up, these will all come out to 6 volts, which is what we expect coming in from the source. Amazing. You guys are on fire solving these problems. You guys are doing a great job. The final thing we want to do before moving on is we want to verify the total current and make sure that it sums up to the current through each branch. So I total is equal to I1 plus I2. Let me redraw that. I2. I2. There we go. So we know that 0.0709 amps was the total current. We got 0.06 from I1 and 0.109 amps. We add those together and we make sure, boom, they are the same. Cool, so now we're going to design a voltage divider. The problem says, design a voltage divider circuit using two resistors R1 and R2 such that the output voltage is 2 volts when connected to a 6 volt DC source. Determine R1 and R2 if their sum is 10 kiloohms. Let's write down everything that's been given to us in the problem statement. So for starters, we're going to write out the equation that we'll be using, right? We'll be using the voltage divider equation. So we have V out is equal to V in times R2 divided by R1 plus R2. There we go. We have our V in of 6 volts and we have our V out of 2 volts. We know that R1 plus R2 is equal to 10 kiloohms, which is 10,000 ohms. Cool, we have everything we need to solve this problem. All we need to do is plug in the values and solve for R2. You'll see. So we have 2 is equal to 6 times R2 divided by 10 kiloohms. So if we keep it with 10 kiloohms, that means our answer is going to have 10 kiloohms in the answer. So now if we multiply by 1 over 6, which is the equivalent of dividing by 6, we're going to cancel out the 6 on this side and move it to the other side. So we have 2 over 6 is equal to R2 divided by 10 kiloohms. Remember your units. Now we're going to multiply both sides by 10 kiloohms to cancel out this term, and it's going to apply to the left-hand side. So now we have 1 over 3. I just simplified that 2 over 6. And then now we multiply it by 10 kiloohms, and that ladies and gentlemen, is equal to R2. So to round things off, R2 is equal to 3.33 kiloohms. All right, so now if we go back to our original equation, saying that R1 plus R2 is equal to 10,000 kiloohms, if we subtract R2 from both sides, we now have R1 is equal to 10 kiloohms minus R2. We substitute R2, and we have R1 is equal to 10K minus 3.33K. So R1 is approximately 6.67 kiloohms. There we go. We have solved the problem. We have found R1 and R2 to get our desired output voltage. Great job. Now let's do a quick check before moving on to the next problem to see that we do get the actual output voltage that we're desiring. So using the voltage divider equation, we have V out is equal to 6 times 3.33 kiloohms divided by 10 kiloohms. And that is equal to 2 volts. 2 volts, exactly what we were expecting. Very nice. The key takeaway here is always, always, always trust your voltage divider equation. When you're using the equation, you can solve for your R1 and R2 values so long as you know what the total resistance can be. For problem 6, we're playing detective. We have a parallel resistance with an unknown resistor. So we have a 6-volt DC source which powers 2 resistors in parallel. One is 10 ohms and the other one is unknown. The total current supplied by the source is 2 amps. So we need to find the value of this unknown resistor. Let's solve this mystery. All right, let's start with what we know first, all right? So we know that our voltage is 6 volts, and we know that our current is equal to 2 amps. We know R1 is 10 ohms, and R2 is a question mark, a big mystery, right? Okay, so we have everything we need to solve this mystery now. Detective, where should we start? Well, we should start by finding the total resistance in the circuit using Ohm's law. So we have V is equal to I total times R total. So we want to find the total resistance in this case, since we know the voltage and the total current going through the circuit. So now we have R total is equal to V over I total. So we have 6 volts divided by 2 amps. So the total resistance in this circuit is 3 ohms of resistance. Keep that in mind. So now that we know what the R total is, we can use the parallel simplification equation to work backwards to figure out what that unknown resistor is. So we have 1 over R total is equal to 1 over R1 plus 1 over R2. So we know 1 over 3 ohms is equal to 1 over 10 ohms plus 1 over R2. So now if we subtract that 1 over 10 to the other side, we'll get 1 over R2 is equal to 1 over 3 minus 1 over 10. Now it's just basic algebra to figure out what R2 is equal to. So now let's get these to the same denominator. We'll multiply this by 3 over 3. We'll multiply this by 10 over 10. And now we have 10 over 30 minus 3 over 30. And that is 7 over 30. So now if we flip that fraction, we'll get what R2 is. So R2 is equal to 30 over 7, which is approximately 4.29 ohms. Great job, detective. We have solved the mystery. Before we move on though, let's do a simple check to make sure our values are 110,000% correct. Using the same parallel circuit simplification equation, we'll see if we get the same resistance of R total equal to 3. So 1 over R total is equal to 1 over 10 plus 1 over 4.29. 29. So we have 1 over 3 is equal to 0.10 plus 0.2333. So 0.33 repeating is equal to 0.33 repeating. Great! Everything checks out. So we have officially and comfortably solved this mystery. In circuits with unknown components, use the total voltage and current values to backtrack. Then you want to plug that into the parallel simplification equation to work your way back to figuring out what that resistance is. We are finally on to the last problem. We have a resistor network analysis problem, and the statement says we have a 6-volt source connected to 3 resistors, 10 ohms and 15 ohms in parallel, followed by a 5 ohm resistor in series. They want us to calculate the total resistance, the current through the series resistor, and the power delivered by the source, or P total. Let's jump right in. So, like always, we want to start off by gathering all the information that's been given to us. In this problem, we know that the voltage is 6 volts. We know R1 is 5 ohms because that is the series resistor. So R1 is, there we go. Now we know that R2 is 10 ohms and R3 is 15 ohms. There we go. Beautiful. Now when finding R total, we first need to simplify this circuit a lot further. So we notice that we have a simplified parallel connection, so we're going to get the equivalent parallel resistance of that part. So our goal is to find R total first. And we see in our circuit diagram that we have a simplified parallel circuit combination. So we want to start off by finding the total equivalent resistance of this combination first. So we have 1 over R parallel is equal to 1 over R2 plus 1 over R3. So we got 1 over 10 ohms plus 1 over 15 ohms. We multiply by each side. We multiply each side by 1 to get the same denominator. We now have 15 over 150 plus 10 over 150. We have 25 over 150. So now if we flip the fraction, we can find out what the total equivalent resistance of that parallel connection is. So our parallel is equal to 150 over 25. So the total resistance here is going to be 6 ohms. Okay, so now we can redraw this circuit in its simplified state. We have our battery connected to the resistor right there, resistor right here. There we go. So now this is our parallel, and this is R1. So now we can sum up the resistances here, because now we have a series circuit, to get the total resistance in the circuit. So our total is equal to R1 plus R parallel. Beautiful. So this is equal to 5 ohms plus 6 ohms, and so our R total is equal to 11 ohms of resistance. Nice job. Okay, the next part says calculate the current through the series resistor. Realistically, this is basically saying find R total, because R total is going through that series resistor and then splitting off between the 2 branches. So let's find I total. So using Ohm's law, we have V is equal to I total times R total. Finding for I total, we have 6 volts divided by 11 ohms of resistance. So our current is approximately 0.545 amps. There we go. So we know I total is coming through here, going through that resistor, and then splitting off between these 2 branches right there. So the answer to question 2, the current going through resistor 1 is 0.545 amps. And now that we have the total current going through the rest of the circuit, we can calculate what the power coming from the source is. So P total is equal to V times I total. So we have 6 times 0.545. And that is approximately 3.27 watts. Before we finish up, to verify that you calculated everything correctly, all you have to do is verify the power equation, since it's dependent on the previously calculated current and total resistance. So there's another equation that we can use to calculate power, and that equation is P is equal to I squared times R. So if we plug in the values that we got in our problem into this equation, we should see 3.27 watts. Let's check it out. So we have 0.545 squared times 11 ohms. And this gives us, lo and behold, 3.27 watts. Therefore, confirming all the other values we calculated in our circuit. Very nice. Great, everything now lines up. When analyzing mixed networks, it's always great to simplify the parallel paths first. Once you have that, you can find the total resistance to find the total current going into the circuit. Then you can use whichever power equation you would like to use to calculate the total power in there. Either one should work. We covered some awesome foundational topics today, like Ohm's law, series and parallel circuits, voltage dividers, and how to work backwards from unknowns. I hope you found this helpful. If you found anything confusing, please feel free to tweet us or DM us at Horizon Robotics Lab. We truly appreciate all your feedback, and we look forward to answering as many questions as possible. One more thing. In the solution set, you should also see a section called Build Along. The Build Along section shows you how to build the circuit in the problem on a breadboard to use your multimeter to confirm voltage, resistance, and current values. This allows you to not only double check, but also triple check your answers and make sure that everything lines up. Not only that, but it also makes you more comfortable building circuits. Well, that is everything for today. Happy learning, and we'll see you in the next one. If you like what you've seen so far, you should visit our website and check out our electronics and coding kit. It comes with all the videos, all the lessons, all the code, all the labs, and all the project files. So yeah, link in the description, and happy learning.